So we're still in the middle of studying varieties x locally at a point. And for this, we have defined both the cone of x at the point A and the tangent space. And we have seen in the last video that the cone is always contained naturally inside the tangent space. And both kind of approximate x at the point A. And now we're going to see the best case here is when you actually have an equality here, when the cone and the tangent space agree. And this means that then x can be nicely approximated by a linear space at the point A. And so we give a name to this good situation. So when x is a variety, A is a point in there, then we say A is a smooth point or a regular point or also a non-singular point. You will find all these three words if you look at the paper in algebraic geometry. We say this is the case if we have the situation CA of x is equal to TA of x. And the less nice case, then A is called a singular point or a singularity of x. And in the very first videos where we motivated algebraic geometry, we have seen such examples of singularities. And then globally, x is called singular if it has some singular point, and otherwise all points are smooth points. Then we say x is smooth or regular or non-singular. And so, for examples, we have always looked at these three different curves. And then in the first case here, this basically parabola, at the origin, we saw that the tangent space and this cone agree, both give the x-axis. And so this thing is smooth at the point 0, and we're going to see soon that it's also smooth everywhere else. And conversely, this case here of this crossing and of this cusp, there we saw that the cone, this is in dark gray, this is just a union of lines in this case, but in light gray, the tangent space is everything, all of A2. So in this case, they don't coincide. And so these are singular at these points. And so this is now the formal notion, what I meant when I said that this point looks a bit fishy or doesn't look very nice. So the correct word here to just say it is a singular point. And let's start by characterizing this a bit more, because in fact we can characterize it purely in terms of the dimension. So when x is a variety, A is a point, then we have equivalent condition that A is smooth there, which means CA is equal to TA at this point. This is equivalent to saying dimension of TA is the local dimension of x at the point A. And this is in fact equivalent to saying that you just have one inequality here, so less or equal. Yeah? And this is now very short proof. So because we have seen that the dimension of this cone of x at the point A is given by this codimension here. And so assume you have A, namely that CA of x is equal to TA of x. Then if you apply the dimension at both sides and you have dimension of TA of x is dimension of CA of x is equal to codimension. So this is how you get A implies B. And then of course the equality here also implies this inequality. So B implies C is also not hard. And the only thing to show is then that C implies A. But we started out reminding ourselves that CA of x is always contained in TA of x. And now we look at what does the dimension, what do the dimensions look like? So the dimension here, again, we use this thing here, is equal to the codimension of x at A. And this thing, the TA of x, is first of all an irreducible space, because it's just a vector space, just isomorphic to some affine space. And we have that the dimension is at most this codimension. And so this means here we have now a topological space whose dimension is bounded by this thing, and it has an open subset, or it has, let's say just it has any subset here. In fact, the CA of x, I guess, closed subset in general, which has this dimension here. And then by the basic dimension theory, it just means there cannot be anything in between there. So you have to have equality, otherwise you would find a chain of irreducible subsets here, which could be extended once more by TA of x. And this would give a contradiction, because then the dimension here would be at least one more than this codimension here. Okay. And so this was just a full proof. So we have characterized it equivalently by saying the dimension of the tangent space must be equal to this codimension here. Okay. In particular, note that if x, for example, is irreducible of some dimension d, then this just means that all the tangent space at all points of x must all be d-dimensional for this to be smooth. Okay, and then there is a short remark connecting this notion of smoothness to commutative algebra. So again, x variety A in X, then we have seen that this stalk of the structure sheaf at the point A, which we call the local ring at A, is actually a local ring in the commutative algebra sense. So it has a unique maximal ideal, which we can call I of A. And then the claim is that A is smooth if and only if, well, the dimension of the tangent space is equal to this codimension. But we have seen the tangent space is the dual of this quotient here. So we can equivalently compute the dimension using this quotient here. So we have this here is the dimension of the tangent space, and this should be equal to the codimension of A in X. And now I want to argue that this equality can be purely expressed in terms of properties of this local ring. And so the left-hand side is already purely in terms of the local ring, because this is the maximal ideal, this is the square, you can take the quotient. This is intrinsically defined in terms of the local ring. Now this codimension here, I claim this is equal to the Krull dimension of this local ring. And so to see this, I mean, maybe this is obvious for you from the things that we have already said, but to see this formally, note that how would you compute this codimension here, or how you would define it is you would say, well, I look at chains of irreducible subsets of X containing A. And we can, I mean, for computing this codimension, we can just choose any affine neighborhood. So without loss of generality, we can say X is affine. And then these irreducible subsets containing A correspond to prime ideals in the coordinate ring of X, which are contained in the maximal ideal associated to A. So here you look at chains of prime ideals, all contained in the maximal ideal associated to A. But then it's a result from commutative algebra that the prime ideals of A of X contained in the maximal ideal associated to A are just the set of all prime ideals of this localization of the ring A of X at this maximal ideal of A. And so somehow these chains correspond to the chains of all prime ideals here. And then the Krull dimension just gives you the length of the longest chain. So I just said this in words, but basically this uses this one commutative algebra lemma that the maximal ideals of the prime ideals of the localization are just the prime ideals in the original ring contained in the prime ideal at which you localize. Okay, but this means this condition here is purely a property of this local ring. This is how we connect it to the commutative algebra. And this notion then is called to be a regular local ring. And then from commutative algebra, one very nice result is that any regular local ring is automatically an integral domain. We have seen, I mean, for affine variety, having the coordinate ring be an integral domain is exactly equivalent to the variety being irreducible. And so having this local ring be an integral domain then corresponds to X being locally irreducible at this point, which means that A lies in a unique irreducible component, let's call it xi, of X. And So somehow there's at most one or exactly one irreducible component of X passing through this point A. And in this case, of course, the codimension here, this is the maximum of the dimensions of all components containing it. And so this is just the dimension of this irreducible component. And then smoothness says the dimension of the tangent space should be the dimension of this irreducible component. So if you turn this around, so this was when A is smooth. So this means that if A doesn't satisfy this local irreducibility, so somehow if there's xi and xj, different irreducible components containing this point A, so if you look at points in this intersection here, then any point in there must automatically be a singular point. And so here you see an example. Here you have one irreducible component of dimension 2, one irreducible component, let's say, of dimension 1. They meet in this point, and then this point must be a singular point because it lies in more than one irreducible component. And so this is a nice criterion which you can check purely from the perspective of intersecting these irreducible components. One word of warning here is that being locally irreducible at this point is not sufficient for smoothness, because we have indeed seen that in the example of this vanishing locus here, this cuspidal curve, this is an irreducible variety. And so this means this origin point is contained in a unique irreducible component, the one given by the entire space, but still it's a singular point. So there's kind of an implication. Being smooth implies being locally irreducible, but not the other way around. So keep this in mind. And then in the next video now, we're going to get some explicit criteria for checking whether a point is a smooth point or a singular point.